So, yeah, I would like to introduce Katie, who is a PhD student in University of Cambridge, and she also spent a couple of months in VMware research doing an internship, and she will talk to us today about Flexible Paxos.
Yep. Thank you very much. So today's lecture is part of the Dr. TLA Plus series. This lecture is going to be recorded and publicly distributed. I'm happy for people to ask questions during the talk, but if you don't want to be recorded, you can save those questions for the end. As we said, I'm Heidi Howard. I'm a PhD student at the Systems Research Group in Cambridge, although what we're going to be talking about today is more of a theoretical result. We're going to be talking about Flexible Paxos, a simple yet, I think, quite powerful result in the field of distributed consensus. So the talk today is divided up briefly into 4 sections. Firstly, an overview of Paxos. I know we've got quite a range of abilities in the room, from absolute Paxos experts to people who haven't seen it in a few years. So I'm going to go through that in a way that I think offers an interesting perspective on the work. Then I'm going to introduce Flexible Paxos. So what's changed? Why am I here? I'm not here just to give you a history lesson in the field of consensus. Then we're going to move on to how we can actually utilize this and make use of it using different quorum systems. And finally, I'm going to talk a bit about TLA+. So how do we know this to be true, and how to convince people that this is the case, and how do I show people the mistakes they might make with it? So, starting off with the background. So, distributed consensus. For the sake of this talk, I'm going to be defining consensus as reaching agreement in an asynchronous distributed system. So that means we're not putting bounds in for safety on how long it takes for a message to traverse a network, how long it takes for a host to respond to a message, in a system that has crash failures. So nodes may fail, the nodes may be unresponsive, but we're not assuming that they can act maliciously or arbitrarily. So generally, the algorithms in this space lie here in this interesting read of a paper. This is Leslie Lamport's part-time Parliament from '98, and it's really shaped the way that we think about consensus ever since. So why be interested in consensus at all? We've had this paper for decades, and people have written many other papers about it. So what I would argue is that consensus still isn't a scalable, still isn't a solved problem. Firstly, because consensus isn't particularly scalable. The algorithms that people tend to use, such as Raft, are usually deployed across 3 nodes, 5 nodes, or if you're really pushing it, you might deploy it across 7 nodes. But the reality is that this is a very small distributed system. Consensus is slow. Having the usual approach is to have a majority of participants agree every time you want to do something in a system, and having to talk to the majority of people just takes a long time. You have to ask them, you have to wait for them, you have to deal with the fact that they might have failed. And thirdly, building on that, consensus often isn't that available. So usually we use consensus to try and improve the availability of a distributed system, but in many of the algorithms that people actually use in practice, they're kind of broken and have issues with liveness. So many people will argue that the price of this is just too high. Like, let's leave consensus, let's go and let's use CRDTs and let's use eventual consistency, because it will never be able to give us the performance that we need from the system. So now I'm going to have a look at the actual Paxos algorithm. I'm not going to describe it in a way that's very true to the original formulation, but instead I'm going to combine it with state machine replication, which is where we take an application and we replicate it and we coordinate operations on those replicas. If you want more on the... Yeah.
Good question. Am I right to more or less identify your critique on the previous slide with Paxos? When you say consensus is not scalable, do you mean Paxos is not scalable? Because it's a sort of dominant algorithm, is that right?
Yeah.
Okay. So it's not, Paxos is not scalable, slow, not available. Fine.
Cool. I mean, a lot of this is fundamental, right?
Yes, well, the point of this talk is that we had Paxos and then we built loads of stuff on it, and we're actually going to revisit the very fundamental idea behind it to change this.
Fundamental idea is that you're going to change the majority quorums by some other type of quorums, Greek quorums.
We're going to change what the quorum intersection requirements actually are. So we have a huge freedom to use a range of different quorum systems.
Okay.
Ruining the surprise there. So we're going to be using state machine replication and multi-value agreement. This isn't the way that people would often do this, but I'm hoping that this is a more kind of understandable one that's more in line with how we actually engineer systems in the first place. So usually when we're talking about this, we have a system that looks a bit like this. We have some servers, there's a log. I've literally used shapes to try and stay away from the details of the actual application that's using this. and we have some clients and they wish to operate on this log. So they send some requests. What we do is we pick one of these and we say, right, you're the boss, you're the leader, the master, the distinguished proposer, the primary, whatever name you want to give it. You're in charge of coordinating the system. So we send the requests, this leader replicates them, gets the responses, and tells the client, all is good with the world, everyone's in agreement, let's carry on. So the question arises here, how many of those copies of that request are enough? In that example, everybody got on board and then we told the client. But waiting for everybody to get on board with the decision is pretty slow. So we need to decide how much agreement is enough before we can proceed. And for this talk, we're going to refer to this as the replication quorum. In normal Paxos terminology, this is also known as phase 2. So think of this as a phase 2 quorum. And for now, although we'll change this later on, we'll assume we're using majorities. So we need 2 nodes out of 3 to agree to this before we can proceed. So what happens when a failure occurs? Here we have 3 servers and the bottom server has failed. Request comes in, leader replicates request, gets the responses and replies to the client. All is well.
Did he just time out? Just to wait to see whether the other guy's going to reply, or
he doesn't even need to do that, as long as he's heard.
I've got 2 out of 3, so.
Yep, didn't even bother waiting. This guy didn't even have to fail, he could have just been slow. So then the question arises, what happens when the leader fails? We can deal with non-leader failures much more easily. So we still have 2 servers in a system of 3, so we would like this to be able to carry on. So let's get one of these other guys to take over. You can be the leader now, you're in charge. But this person cannot start just randomly replicating requests. Firstly, we don't know for sure that old leader has actually failed, where maybe there's a timeout and we've said, oh, they haven't answered us, so we're going to assume that they failed, or they may be behind a network partition, but they may still be there, and they may cause damage to the system in the future. And as we can see here, this leader doesn't actually know about all of the requests that have been committed so far. So when we're talking about distributed consensus, the first and foremost thing is always to never compromise safety. So once we've told a client, yep, we've done that on your behalf, we've put the place for, we will never go back, we will never overwrite that. So before this new leader can take over, they have 2 jobs they need to do. Stop the old leader and find out about what's already been committed in the system. And the ordering here is important because you want to stop the old leader so you can essentially freeze the state of the system and then learn about what's happened before you take over. If you did it the other way around, the old leader could come along and change the state of the system. So, first job first, we need to stop the old leader. A simple solution to this would just be to ask them to stop. And in some systems where we actually preempt the old leader for performance reasons, this is a useful solution. Another solution that we see being used is to use leases. So when you become a leader, there's a time on that. You're the leader, but only for the next minute, and then you have to renew that, otherwise you've lost that privilege. But that relies on clock synchronization, which we're trying to avoid here.
Not really, right? It relies on bounded drift in the clock, right?
Yeah.
Which is a bit different.
It is, yeah. Partial clock synchronization. So the third approach would be to have to speak to other nodes in the network. So there's an old leader, a new leader, and some nodes. To actually speak to the other nodes and get them to basically promise to ignore the old person. Recognize me as in charge. I appreciate what morning this is. This is a difficult conversation to have. Recognize me as being the leader, ignore this other person, and even though they may still think they're the leader, if they come to actually do any replication in the system, they will not have any power. So we accept the reality that maybe multiple people may think they're the leader, but only at most one of them will actually be that. So if I'm taking over as the new leader and I ask everyone, I am the new leader, please recognize me as such, again, we see the same problem. If I can't ask everybody and wait for everybody to back me. So the question.
Under item 3 of the previous slide, are you now following the 3rd bullet?
Yep.
You're
following the
number
3rd.
3.
Yep.
Okay, fine.
Yep. Those 2 are other techniques with different algorithms. So the question arises yet again, how many promises of people who say they're going to back me and they're going to ignore these old leaders, how many is enough? We're going to refer to any group that is enough as the leadership election quorum. This is the phase 1 quorum in typical Paxos terminology. And previously we said we're going to use majorities for replication, so we can use majorities for this again. So if I'm going to take over in a system of 3 and 2 people have backed me, and there's an old leader floating around, they won't be able to get 2 people who still back them as a leader to do work. So when it comes to actually making these promises, we need a mechanism to break them. So if I'm going to step up and say, I'm the leader, everybody back me, ignore this old person, I'm in charge now. Eventually there's going to come a time when someone's taking over from me. And we need to allow people who've made promises to basically renege on those promises and to back someone else in the future. And we need a kind of deterministic scheme to do this. And the way that we do this is we have some kind of value when we become a leader. This can be called proposal number, ballot number, view, term, or epoch number, depending on the algorithm that you're looking at. And it basically just means an identifier that's unique, that says, you know, I am number 4, vote for me in 4. And when people back me in number 4, what they're actually saying is, I back you right now. I will not listen to people with lower numbers, so 1, 2, and 3, they're history to me. But I would back people with higher numbers. So I'm basically agreeing to back you right now with a kind of built-in promise that I will be able to go back on this in the future. Okay, so the second part of this was learning the old entries. So you have this new leader, they want to go around and speak to the nodes in the system and find out what's happened, what entries do you have in the log. So what we can do is we can go around and we can ask a group of them. Again, we can use this leadership election quorum because we know that's going to overlap with the replication quorum from before, and say, tell me about what's in your log. Now there can arise a situation where 2 different machines may give us 2 different answers. One may say, I have a circle here at index 3, and another may say, I have a square here at index 3. And you then need to decide which one of those you're going to listen to. And here we can use that breaking promise mechanism that we saw before.
Can I ask a tiny question? Your terminology is starting to depart quite a bit from the paper you cited, and actually the other papers. So, for example, you know, Paxos has votes on slots. Sometimes there's a particular leader for the even ones, and so on. But I'm wondering, is there a specific Paxos protocol that you're actually going to turn out to be focusing on, a well-known published one? Or are you working towards a different Paxos protocol at the end of the day? You commented that you weren't really going to be focused on the classical one. You do tell us what you actually are focused on.
So the difficulty is that there is the original Paxos protocol and its terminology, and then there's a whole host of things that are built on that and have their own terminology. The stuff I'm talking about here actually applies to all of these algorithms in this space. And so I don't want to get caught up in the terminology of one algorithm and say, this is an optimization to Raft. I'm going to use all the Raft terminology and talk about it like it's Raft. And again, and the original Paxos terminology can be confusing for people. So that's why I've kind of tried to...
Does terminology match one-to-one to any protocol, any of the standard protocols that comes to mind for you?
One-to-one? No. Because they don't usually differentiate between the 2 different types of quorums, which is important for the next part.
It's really been doing a great job of naming all the different ways that people have named the different concepts, views, epochs, terms.
There's a lot of different terminology out there. It's a bit of a maze. Okay. So where we see conflicting requests, we can use the idea that we had before about how you break promises to determine which one we're going to use. So if I see these 2 different requests and one of them was replicated by leader ID 5 and one was replicated by leader ID 7, I can say that only the 7 one could possibly have ended up being committed. The one that has a 5 cannot have been committed because at some point before that 7 one was replicated, number 7 had to become a leader. They had to talk to their replication quorum to get that agreement, and they would have found out about that request and would not have put a different request into that slot.
And you can't have 2 that are both at number 7 but have different payloads?
No. So you cannot have either one node saying, it's a triangle, and then saying to some other people, it's a square. That's Byzantine behavior. And in terms of having different nodes doing that, the requirement for this is that the ID is unique. There's different ways of implementing this. You might do ID of the node concatenated with the highest ID that you've seen so far. You could allocate it round robin, protocols like Raft, you actually build into the election process how we decide what the unique ID is. Okay, so that core mechanism is what is commonly referred to by people as Paxos. That is not what was written in the original part-time Parliament paper as Paxos, but this is when people say Paxos, this is usually, when engineers and stuff are referring to, this is usually what they're talking about. But we see this idea recurring again and again in the literature, from view-stamp replication in 88 to the recently popularized Raft. So we've done all this work, what does it actually give us at the end of the day? It gives us safety. We say once there's a request, say we've put it in this log and we've told the client, this is the request, we've committed it, we've put it here, we're not going to renege on that point. We're not going to put something else in that index. And in terms of progress, we say, well, if a quorum of nodes are up, then we can, and they're communicating, then we can make progress. In practice, it's a little bit more complicated than that. There's some partial synchrony assumptions that we need to make for that, but broadly, that's the idea. Before I move on to the new material, is there any questions on that bit?
Is membership static or dynamic?
For the sake of this talk, membership is static.
I think there's a family of Paxos-like algorithms.
Yeah.
Has anyone won, or do they all have slightly different trade-offs?
They all have many different trade-offs. If the definition of one is most widely used in practice, I would say Zookeeper had one. People are now dropping Zookeeper in favor of Raft consensus, which is an interesting decision. But there's a huge range of things in the literature. And there's much better algorithms in the literature than what we see being used in practice.
Yeah,
it's
all the same.
So, as much as this has been fun, I'm not here to give you a history lesson. I'm here to talk about new work. So what's changed? This has been around for decades. This is the paper that I wrote alongside Dalia and Sasha at VMware. So for a long time, it was thought that all quorums in Paxos, regardless of whether they were being used for the role of replication or for the role of leadership election, needed to intersect. Therefore, majorities are a sensible scheme. But when you look at the algorithm more deeply, it becomes clear that this is not the case. We only need leadership election quorums and replication quorums to overlap. There is no requirement that two replication quorums overlap, and in most algorithms, there's no requirement that two leadership election quorums overlap. Now, I understand that this idea is quite controversial and new, so I'll let it sit for a little bit before we go into some detail. So the implications of this result, if it's true, which I hope to convince you that it is, firstly, it helps us understand Paxos. I try teaching this to undergrads to see a sea of confused faces again and again. And if we can understand the requirements a bit better, maybe we can teach it a bit better. For the theory people, it's a generalization. It's an observation about a very old and widely adopted algorithm, and it's a weakening of the requirements. Neatly is quite orthogonal to many of the variants that we see in use today, and therefore making it, whilst a simple result, quite widely applicable. In practice, we can now use many interesting quorum schemes. So it was always the case that we could use different quorum schemes. We didn't have to use majorities. But if all the quorums have to intersect, majorities are a sensible one. That's what we see being used in practice. So what are these new quorum schemes? What are these new systems that we can now construct? So what we can do is we can look at the literature on things like commit protocols, on data replication, on databases, where we see things like read-write quorums or commit-abort quorums, and we can now apply all of that research to the field of distributed consensus, now that we know that we don't have to have all of the quorums overlapping. Go for it.
Why is it obvious that if they all overlap, then the majority is the right thing to use?
So if they all overlap, you can have alternative schemes. Like you could, for example, on a grid have like a row and a column, but majorities give you a one overlap. So it's simple. It's not the best, but it's what everyone seems to use in practice. I still haven't managed to find anybody who uses a different quorum scheme for Paxos in practice.
So I'm trying to understand why you're playing this into tautology, basically. So if I go back to the way you stated this, it seems to me that this centers on the notion that there's a single elected leader, because Yeah, in classic Paxos, there's tension among multiple leaders that independently assert that they're leaders, and it's sort of why. So you've sort of implicitly shifted us to Paxos with a single elected leader, at least for a particular slot. Is that right? And then I'm wondering why that single leader would want multiple non-intersecting, what would be, is that the answer you just gave a second ago? And why would that one leader want multiple non-intersecting replication quorums? Is it because the updates themselves are commutative, they commute in some sense, or they're independent? Is that what you have in mind?
So the advantage of having non-overlapping replication quorums is that you now, when you, in the common case, you're doing replication, you now don't have to wait on the majority of people to agree with you. So if you only have a replication quorum of, say, a third, you wait for less responses and send less nuggets.
I'm just trying to understand, this statement doesn't seem like it makes a lot of sense to me unless there's just a single leader. But if there's just a single leader in charge of the sequence of slots, why would it have non-overlapping, why would it want to do that? So it's the point that maybe one guy's updating X and one's updating Y and they have nothing to do with each other, so the leader chooses distinct non-overlapping quorums. Is that what you have in mind?
So this does apply to the standard Paxos where you do have multiple leaders fighting for each other. The reason I've kind of focused on a very leader-driven way here, just for explaining Paxos to people who are unfamiliar in the audience. I think the idea that I'm going to try and get across in the next section is that the leadership election is rare and the replication is common. So we can put a bit more work into the leadership election and cut down on the replication. We can revisit that again in the next section. So now we're going to borrow from the literature and apply some interesting quorum systems to Paxos. So going back to what this gives us, in terms of safety, we stick by our claim that we're not going to compromise safety. In terms of progress, we now have a bit more of a fine-grained notion of what it means to make progress. So previously, there was one notion of quorum. Quorum up, system up. Quorum down, system down. Now we have a more refined notion of this. So if the leader's up, so if we're happily doing some replication, as long as there's a replication quorum around that we can use, we can make progress. We can commit requests.
Can I start that from you
Yep.
said earlier that leader election quorums don't need to intersect with each other. Is that true?
That is true.
And you're going to use that?
I will use it in one of the examples here. I think for most practical systems, you would want them to overlap because you want, for example, you don't want to confuse clients by telling them I'm in charge and someone else being like I'm in charge. And specifically for Raft and ViewStamp replication protocols and their derivatives, you do usually need the intersection because they use the intersection to check that the ID for leadership is unique. So when the leader's down, if we have a quorum that we can use to elect a new leader, we can then do so and make progress under the first requirement.
So does this go all the way? The replication quorum could be 1.
It
So
does
you just
go
talk
all
to
the way.
leader, he says, fine, go for it.
Yep.
But then somehow number 2 is going to be really expensive.
Yes, so if, as I'll show you in a sec, if you do that and replication quorum is 1, everybody has to be involved in leadership election.
I see. So there's a sort of knob you can move between
Yep.
these two.
There's even a formula that shows it.
But in practice, if you're doing set machine replication, you lose the state, right? So there's a bound on the number of failures, right?
Yeah, so
the
it's,
size of the quorum you contact for the replication.
for most of the things here, it's a matter of choosing which trade-offs and compromises you want to make. That's why it's called Flexible Paxos in the first place.
Assuming that you don't lose data, I mean, the number of failures is the minimum size that you need to contact. So leader plus F minus 1, right?
Can I do this next section and revisit that? So this is the scheme that we've always had, strict majorities. So we have a system of 5 nodes. Here's 3 little examples of it. And you need 3 of them to get on board to do either replication or leadership election. And the thing about these 3 is they're always going to overlap. So the first thing that we can do with this new result is say, well, what happens when we have an even number of nodes? When I talked about it before, we had 3, 5, 7. What if you have 4? What if you just happen to have 4? That's how many machines that you've been allocated. Well, with strict majorities, you'd have to speak to 3 of them to do either replication or leadership election. but we can do better than that. When it comes to replication, we could just speak to 3 of them. And when it comes to leadership election, we could talk to 4 of them as we did before. So what we've done here is we've reduced the cost of replication. We've reduced the size of that quorum by 1. Now this isn't a huge change, but it's interesting, and unlike the other systems, which are a matter of making trade-offs, I would argue that this is just a win-win in this scenario.
Even though people use preferred quorums, right, where you talk with, as I mentioned, right, assuming that you don't want to lose that, then you need to contact, the leader needs to contact F-1 nodes, right? People have matched that lower bound, right?
Sorry, I didn't catch that.
People have matched that lower bound already, right? You contact only F-1 guys as a preferred quorum. You don't even need to try to contact the other ones, but you will if you don't get replies from your preferred quorum. Right?
Yeah, so when we're using quorums, we don't have to talk to everybody. We can just talk to the people that enough will be sufficient, and then if they failed, we can retry. Yeah, and that's a useful way of applying this technique to then see better throughput. So you don't have to message everybody, you can just message an increasingly small set of people.
Yes, I'm just trying to understand. We'll talk about this.
Okay. Sorry. Pardon?
You going to show us the learner protocol?
The learner protocol.
How to read the data out?
I can talk a bit about it at the end, but there's not already in the slide deck. So in this scenario, we're now talking to 3 nodes when we do replication. This means we don't have to wait on as many nodes, because previously we would have had to wait for 4 to answer us. But we've not seen any increase in the leadership election quorum. So what we can also now do is if 3 nodes fail and we still have the master, we can carry on and we can make progress, which was a failure that we weren't able to handle when we were still using strict majorities. Okay, so another scheme, and this scheme is a bit different to the existing ones, pushes this result really far in one direction. It says, okay, let's get everyone on board when it comes to replication. Let's make everybody participate in replication. When it comes to leadership election, anybody can just step up to become a leader straight away. They don't need to do any network communication at all.
Don't they need to somehow prevent other people simultaneously electing themselves?
So it could be a scenario where everybody simultaneously elects themselves, but then when they come to do any form of replication, only one of them will win. So it goes back to this idea of many people can think they're the leader, but at most only one of them is actually going to have the power to execute on that. So this has some interesting parallels with chain replication, where we, with the help of some kind of auxiliary for membership changes, we can handle F failures out of a system of F+1. So this is the formula I mentioned. So what we can do now is we can trade off the size of the replication quorum and the leadership election quorum. As long as we meet the requirement that the leadership election quorum and the replication quorum will overlap, they can be whatever size you wish for them to be. Now there are trade-offs to be made here, but the idea here is not to say, here is one alternate quorum system and we should always replace all majorities with it because it's best in every scenario. But instead, that there's the flexibility here to do this as you choose. Maybe you're willing to make a small sacrifice in fault tolerance for a decent improvement in performance. So here you can see, that formula translates to majorities, strict majorities, etc.
Can you do this dynamic?
So doing it dynamically is essentially part of what I'm working on now.
You need a consensus about that.
Yep. Ideally, you can use the consensus you already have to reach consensus on that, but that's a deep hole. So here's another example. So we had 6 nodes, and strict majorities said you have to use 4 of them for replication. Then non-strict majority said, okay, you can get away with using 3 of them. Now we can push it a little bit further and use 2 of them. So we're only talking to 2 of them when we do replication, and we spend most of the time in a protocol doing replication, because we'll replicate tens of thousands of replications, and then the leader's going to fail, and we hit a leadership election phase, and then we hit a replication phase. So what we've basically done here is we've pushed the cost of the replication into the leadership election. So you pay a penalty in leadership election. You now need 5 nodes to agree when you're electing a new leader.
Another penalty, which is if both of those two nodes crash, you've lost a lot of the log.
So whilst the leader's still up, then you're okay. But if the leader is one of those two that fails, then yeah.
So making the replication quorum smaller has a different trade-off.
That's why I was asking about the read protocol.
This one?
That's why I was asking about the read protocol.
Oh, okay.
How to get the data out.
Right.
Yeah, but
So we can apply this again with different numbers. It's essentially, whatever combination of quorum sizes you want, you can have them as long as they meet that requirement. So now I'm going to go on to talk about some more interesting quorum schemes, again borrowing from the data replication literature. So far we've treated all nodes equally. We say, we're counting the number of responses we get. It doesn't matter who gives them, we'll just count them and check that they're there. But in practice, nodes aren't equal, right? If they're in the same rack, they're more likely to fail at the same time, for example. Maybe some are more congested in the network. So if the nodes themselves aren't equal, let's not treat them equally. Let's start differentiating between them. So here's a scheme that does that. We've called this, for generality's sake, groups. So what we do is we have a system here of 13 nodes split into 4 groups. So you can imagine each group being a rack, for example. When it comes to replication, we say, right, let's get one member for each group on board. That way we've got our data split across these 4 racks, for example. And then when it comes to leadership election, we just need to get all of the members of one to be on board with us to elect a new leader. So what we've done, in a sense, is we've reduced the number of participants needed for replication and for leadership election by being more specific about how we actually compose those groups. And you can do all sorts of variants on this technique. For example, you could say you need a majority on each rack, and then you only need the majority on one. You can do, there's all sorts of combined schemes that you can layer. And a lot of this isn't new research, it's just borrowed from data replication and other fields.
So in this case, you don't have the leader election quorums intersecting, right?
This one does not have leadership election quorums intersecting,
So
yeah.
what mechanism are you going to use to stop people accepting stuff from other people?
So they won't, in terms of safety, even though multiple people may think they're the leader, only one of them will be the leader because they'll have this unique ID, and it'll be a highest ID wins, basically.
It's back to the question about all in. This is the same as all in, isn't it, really?
Yes, this is a layer, this is a composition of 2 variants of all in, basically.
The ID generation becomes, if you don't do it right, you get a liveness problem. But if you do it right, you're fine. Is that the idea?
Yeah, although in theory, you should always have been doing the ID generation correctly with Paxos and with the variants. But you can, the point is just to show a couple of examples.
You can't do it as part of the leader election anymore.
Not with this one example, but you can come up with variants of this where you still have that with that overlap. It's just to give you kind of a snapshot of a few different quorum systems, but the whole idea is it's flexible. You can use whichever one is best for you. And there's a huge literature that you can basically take these straight out of. So another quorum system, which is mostly just interesting in theory, I don't know how much use such a system would be in practice, is to split the nodes into a grid and say, okay then, any column is a replication quorum, and any row is a leadership election quorum. So this has the nice property that you don't ever have 2 replication quorums overlapping, and you never have 2 leadership election quorums overlapping. So you should maybe think about a scenario where this might be useful if you're trying to kind of split your requests across the sets. But predominantly I show this because when we come later to model checking, this is an interesting scenario because you never waste time looking at quorums that accidentally overlap. You know that different quorums will not overlap.
Well, previously I'd always assumed that the leader was part of the replication quorum.
So
Which you're right in your initial slide, but maybe that's not necessary.
So it depends on the system. Often with protocols that use state machine replication, the leader is part of the replication quorum, but with some of the newer protocols that we've seen in this space, things like Corfu, they actually say, right, the leader's got a lot of work to do, so let's put them on a separate host that's dedicated. Maybe it's even down to just being a sequencer. Let's put that on a separate host, and then let's keep the nodes separate.
So I hate to do this too, because asking someone to remember a definition on their feet is tough, and I don't know if you have it on the slides, but I'd be curious if you could just give the most formal definition you can of the leader in this model. I mean, how do I know, here we've got 3 non-intersecting leader election quorums. Clearly there's a correctness constraint. So how do you formalize this?
I'm not sure how to answer that, to be
But
honest.
you did the verification, so there must be a formal spec of what it means to be a leader. You know, what
This
it
is the
means to be
same. I feel maybe my approach to trying to explain this is confuse people who are already familiar with this. This is the same. We use the same informal terms. We use the same terminology as Paxos. This is just proposers, and we split out proposers and acceptors, etc. accordingly. And the details of all of that are all in the paper. And there are many more schemes. We can combine these schemes at will as you choose, as long as you meet the requirement that the leadership election and replication quorums overlap, and if necessary, leadership election quorums overlap. So lastly,
the leader election quorums definitely won't overlap.
yeah, they definitely won't. And if you're
So that wouldn't work.
this would work fine for Paxos and many of the variants. It's just some of the newer systems like Raft and ViewStamp replication do need that requirement to ensure the uniqueness of leader IDs.
It's actually as old as Paxos.
Pardon?
Your stamp replication is actually as old as Paxos.
It's older than Paxos.
Yes.
It's yeah.
Actually, it's not older. I did it at about the same time. But it's older than it's definitely much older than the first publication of Paxos, right?
Yeah. In terms of publication date, it's almost a decade. So as I said, we can combine these at will. So the last section, I'm going to just quickly talk a little bit about TLA+. So the reason I was actually asked to speak here today was to say how did I, as not an expert on TLA+, make use of this tool, and that's why I'm here as part of the Dr. TLA+ series. So the reason for using TLA+, mostly in this particular project, is like, okay, we have this result, and we know it to be true. We need to convince other people that it's true, and we need to explain to other people, you know, these are quorums that are okay and these are quorums that are not okay. So TLA Plus is a useful medium for doing that. It's a tool for specifying systems, and then from that specification you can go on to model check or to prove properties of the system. For this talk we're just going to be focusing on the top 2. So, pardon?
You do actually have a mechanical proof.
A mechanically checked proof?
Yeah, of the flexible Paxos is sound.
No, not a mechanically checked one.
You've got a model checked.
Yeah, we've got a model checked,
So up
and
to
we
some size, you know, it's okay.
yeah, and we've got it all written out and published and stuff.
Okay, so I have one question. You said that you're not an expert on this. I know that Dahlia hates TLA+. So that leaves 1 person out of 3. How do you know that his spec corresponds to your protocol?
Peer review. This is what I took Lampport's original one. I didn't make that many changes, for starters. We published it straight away. The spec clearly.
That's kind of an unfair question.
Well, I guess my real question is, did Alex model check your code?
It
or
was
did he
okay.
model
No.
check-
That I did this work. This is model checking that I did. This is not Alex's work.
So did you model check your code, or did you model check a description of your code?
You specify the system, and you model check that specification. We also implemented it separately, and that is a worry. And I'm currently dealing with the fact that whilst we're happy that this is safe, people will then go away and implement that in their favorite programming language, and there are all sorts of actual bugs in that.
Yeah, that's exactly where I was heading with this.
Okay, I actually have a slide on that already.
Yes.
No, the work on iron, whatever it is. Iron Fleet is actually, the code is checked as opposed to.
I see. So,
Okay, so basically what I did is took the original specification for Paxos, and I also did this for Raft, and modified it. And the aim here was just to take Lampport's specification, make the minimal changes necessary to reason about the properties that we want to. And then we go on to model check that. So I'm going to do a very quick demo if everything works out okay. Okay, so this is our variant of the original specification. It's only 91 lines, so it is fairly succinct. It is, taken out of Lamport's book. It doesn't cover liveness, for example. This is purely a proof on safety. I appreciate if you're not familiar with it, the syntax is a bit challenging, but...
It covers leadership elections and replication and all of that?
So what this covers is single value agreement. So instead of looking at, we're doing a whole log, it focuses on one slot. So one person becoming a leader and replicating in that slot. We can do it over a longer thing, and that would result in a longer specification, which we're then less likely to trust to be correct. And also time for model checking this is a big problem. And so keeping it as small and succinct as possible is really important. So you can see at the top here, this is basically the revised assumption. So here it's called phase 1 leadership election, phase 2 replication. And so what we do is we refine the thing. So previously there was just quorums. Quorums have to overlap with quorums. That's the requirement, and it was quorums throughout. Very simple change. It's no longer quorums, it's quorum 1, it's quorum 2, and we have the requirement of intersection that we spoke about. And the property that we're looking to check, essentially, is once a value has been agreed at a given ballot, show that there will never be execution where in the future, for a higher, ballot, leader ID, there will never be a time where we pick a different value. In fact, we're never even going to get to the point of proposing a different value. And that's what these 3 brief lines say. So the stuff in between is just the specification, largely unchanged from Lamport's original. And this is part of a series, and one of the other speakers in the series basically went through this line by line, explaining what each line did. So yeah, this is the requirement that we want to show, and as I said, quorum 2 is for replication. So I'm going to run a very quick test. What I'm going to test, and I appreciate this is a really small model, I just want something fast enough that I can actually run it live, is this pairing of quorums. So this is essentially the grid. This is a 2x2 grid, where you have 4 nodes, you've got the rows and the columns. And I've had to put bounds on the ballots and on values so that I can actually show it to you now in real time. In practice, you don't allow only 2 ballots. But state space explosion is a pretty big problem when using this system. So sorry about the wall of text. I'm going to run it live here. So basically, I've ran the checker here. I'm hoping this all works. Yay! And basically what it's saying is, yep, that's okay. We didn't break that invariant. What I'm going to do now is I'm going to break that invariant. I'm going to remove that node. So this group now only has accepted 2, which means it doesn't overlap with this group. So that replication quorum does not overlap with that leadership election quorum. And what I'm also going to do to make it kind of break properly is I'm going to cut out this assumption, because otherwise that assumption will just fail. That assumption is useful for basically kicking out incorrect quorums at the beginning before you even do the checking.
Before we get that, could you rewrite it just like this? Because I've always wondered
Yeah.
what TLA outputs when something breaks in a trivial way that way.
Should be extra fast.
I've actually never seen somebody run TLA in real time.
So error assertion line 6 to line 8 in TLA plus is for false.
So it's reasonably clear what it's complaining about. That's nice.
Yeah, and it's basically if you put the wrong quorums in, it's going to fail. It's nice to have the assertions to fail that fast and that clearly. But what I will do, and I'm going to hope that this works, I'm going to cut that assertion out and actually have it properly fail. And there we go. So I appreciate it's just a bit of a wall of text, but basically the takeaway is it's given me a sequence of executions that this is all the state of the system that will lead to an assertion, a failure of that assertion that we saw at the end. And if you go to on the slides and on the .TLA++, all this code is open source as well as the models and everything for trying. So this is the slide I mentioned earlier. What's the point of it all? We took Lamport's fairly elegant description of Paxos. We made some changes. We've verified that under certain conditions, the safety isn't violated. And we published this work and we told people about it. People started implementing it. And lots of problems occurred. People started implementing it incorrectly and saying, "Oh, I found a safety problem. It's not true." And then you talk to them about what they did, and you start looking at the code, and you realize they wrote to disk, but they didn't wait to get an acknowledgement that that actually had happened, and so then the machine failed, etc., etc. And if there was one kind of call to action from my experience of using this tool, other than issues with kind of state space explosion, is I would really love more tools to kind of bridge that divide. That's probably going to come out of the programming languages space, but this is something that worries me. So in summary, when it comes to Paxos, the only quorum intersection requirement is that the leadership election quorum and the replication quorum overlap. Majorities are not the only option. There's a huge range of options, and what I would argue is that some of the other options will probably give you better performance in a practical deployment scenario. We can actually have scalable consensus. You don't have to give up on strong consistency and go for these weaker guarantees. TLA Plus is a useful tool for reasoning about systems, but it certainly has its limitations. Okay, I'll take questions, and then, yep. All right.
That was a great talk. I know nothing about Paxos.
Thank you.
So can you, the spec looks very small. Is it not possible to just formally verify it and prove it correct once for all, rather than rely on model checker?
Yes. That's a matter of me learning how to do that and applying that.
People done that for Paxos itself, the original spec.
As far as I know that Lamport has done that, and I'm looking at the other speakers in this series, I don't know that many other people have been able to validate that one for Paxos.
No, I don't think that's fair. There have been a huge number of Paxos protocols proved correct. As you said earlier, they're all proven correct. The trouble is that you don't know that the code corresponds. So the point of this path is to do the kinds of things that that Arnfleet did, where you reach a point where you do tweak the code correct. Because these model checkers can eventually bridge the divide and use to check C++. But there's actually at Oxford, I know Cambridge is supposed to mention Oxford, but there is actually a model checker for C and C++. It doesn't cover some of the more advanced C++ features, but it's a model checker that could potentially implement this protocol in C++ and then potentially use that model checker to check it.
So this
I think that's
model
the
checker
trajectory.
does not prove correctness, right?
Yeah.
You find bugs, right? Unless you can exhaustively search the space, which usually you cannot. You might sometimes exploit symmetry.
If you
And it
have
still makes
some kind of
assumptions of what the
state-
story system.
Right.
So we're still assuming this
So
might have
what
some
is the
very
state
simple.
of the art in machine check proofs? Because yes, people have proved a lot, but not many people have done machine check proofs in TLA plus, right? Is there was this thing called TLA P something proof of system?
Yes.
Yes. Was it
Yeah.
yes?
I'm not familiar with that, but
But I don't think
Have a look at
many
it.
people use it. Right? So in terms of machine checks,
Pretty
TLA
popular.
proofs.
Constable talks about that work a lot. I think there's a huge body of people. So getting back to the speaker, so, what do you think of the broader problem of how to? I liked your talk, and I'm not really asking a question about your talk. I'm asking you to speculate. What about the broader question of how to build tools to help application developers who want to use a Paxos protocol in a setting that maybe has novel hardware, for example? What are the prospects for offering them help to figure out if they're getting it right? Because you were talking about somebody breaking Paxos just by implementing it on a disk and not realizing that there's a synchronization obligation. But it could get worse. I mean, I could use Paxos in a setting where I'm dealing with some kind of an external structure, and that's where the obligation is. So what's going to happen? What do you think is going to be there 5 years from now? Not even infinitely far, just 5 years from now.
in terms of what I think there's going to be, I think we're still going to see a lot of bugs and issues. In terms of what I would like to see, I did in previous work use a tool called SBL where I basically specify a state machine, and then you can import that into a Promella for spin and model check that. And then you write your normal application, and basically you can run the two alongside each other and say, this is my application, it's application code, it's performant and stuff, but can you just check that it's how it's acting in a simulated environment is in line with the model? That's not to go as far as a formally verified implementation, but that's kind of the best I've seen, well, the best I've actually used in terms of making stronger guarantees.
Seems better, right?
Pardon?
If you look at Ironfleet,
That was just what I was going to ask.
Not yet, but I've heard good things about it.
because it does seem better in the sense that it will produce a proof. It makes some assumptions. It doesn't produce proofs all the way to the hardware, right? But it does produce proofs based on some kind of formal model of language in that.
Do you know Daphne? That's what they use. It's a version of Java with assertions. It's quite nice, and it's a model check. So does the specification of Paxos take a form that an external user of Paxos could treat as a kind of a module? Right? If I use Paxos, I'd like to be able to say, because I use Paxos, I know this is totally lettered, and I know it's consistent. Does that specification have a form that I can use as an artifact, or do I have to actually use the whole protocol as a kind of a module in my application?
I don't think so at the moment, but I think it would be possible. Yep.
I like the talk. I'm a bit concerned, as I think somebody mentioned during the talk, about what leader means.
Yeah.
I mean, with the straightforward requiring a simple majority for leader election, it's pretty obvious that the system is likely to end up with a leader, and the leader is actually capable of getting stuff done. Whereas in this system, it's clear that you don't end up with two leaders who are both capable of getting stuff done, but the chances of you having many leaders, none of whom are getting stuff done, you know, I mean, I understand, of course, that you're looking at the whole potential spectrum of what's possible once you've added the flexibility, but it does seem that kind of going beyond the majority style way of doing legal election does seem to perhaps be more practical.
I completely agree. I think it's, from a theoretical perspective, it's nice to know that if you're using some of the Paxos variants that you don't need to have this leadership election overlap. Like that's an interesting property. In terms of practical uses, when I have presented this talk to kind of developer conferences, I've just kind of not mentioned that you don't need it. It causes too much difficulty, and just said leadership election quorums also overlap.
Does leader, as an actual thing, does it show up in the spec?
This is single valued, so a leader is essentially someone who has received enough 1B, which is the response from vote for me as a leader.
And you have one that's not single valued, where it gets fancier and where you have to actually express that?
Not that I can show you right now. Yeah.
Can you back up to your previous slide, the conclusion slide, before the question slide? You say here, the third bullet, don't give up on strong consistency, distributed can be performant and scalable. So, but the whole protocol seems to say, if I'm implementing a distributed database, I always have to talk to the leader, right? And the probability is only one, right? So the leader's going to get really hot. I thought the whole point about all these distributed storage systems, key value stores, blah, 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 weak consistency is that the leader gets too hot and we always want to talk to him or her. Right?
I'm so pleased you asked that question.
It seems a little bit, tell me about this bullet.
Prior to doing this work, the work that led me to do this work was some work I was doing about how do we dynamically delegate work away from the leader such that the other nodes in the system can equally share the burden of doing the replication and basically reducing the role of the leader to a point of serialization. That work kind of got put onto the back burner when this stuff came up.
So
but
bullet number 3 is a bit speculative at the moment.
Yeah.
You're saying that if something else works out about this delegated leadership delegation, then maybe we can. That seems plausible.
There is other work in leaderless consensus.
For example, right? is the same with here. You can use something like primary backup replication. So you need F+1 replication, don't write F faults, right? And then you can reconfigure. She alluded to that in the talk, right? And then you use consensus, but only when you reconfigure the system. Only when you want to put people out of the system.
So this is not used on the data path, this is just on the failover to control the failover. That's how you get performance.
And you
Oh,
can-
even the replication part is not used on the data path?
Yeah.
Oh,
No, the replication is.
Well,
Well,
this
so
would
not
you-
replication,
where
it's
you
chain
can shard the data across multiple farm. Farm does this, for example, right? And many other systems do it. So you shard the data across multiple guys. You can do transactions across those guys, and you only do consensus when there are failures to move people out. Other people, like Symfony, ATTS, lots of other systems.
But yeah, that is essentially a speculative statement saying when you combine it with existing techniques, I think we can do good stuff. Yep.
So I guess you've got a paper proof that it's correct for all.
Yeah, that's what's in the paper.
And often if you make a proof, if you weaken like an assumption, the proof actually gets nicer. So is the proof prettier than the original proof? That's not good.
I don't think I'm capable of producing prettier proofs than Leslie Lamport's.
Very cool.
But, I would say the spec that she showed us is playing the role of that pretty proof, right? Because after then the model checker just does its thing and either admits bad cases or it says it checks. And that spec is actually very readable.
No, Claudia was asking about the paper proof for all configurations, not just the model checker.
Well, but this is exactly what Miguel touched on, right? For that proof to have been a real proof, you would have to have an argument that in fact the model checker was able to sort of enumerate equivalence classes of a full reachable state space. But then you would have a full proof, and that's the argument that Leslie tries to do.
We have used
one
model
way,
checker.
right?
You just use logic to prove it by
Right.
logic. Then you have
This is actually what Leslie tried.
Well, sure, but that's what that model. I mean, in fact, there's a new Perl constructive proof of a Paxos protocol, and that's a complete proof. I mean, and including the conditions under which it's live, which become a sort of weakest precondition. I don't think they can automatically generate that weakest precondition. But so that would be very much to your taste. Model checkers at best are going to be bug finders, except if you can, say by checking the following enumeration of states, you will have checked all reachable states. Right? That'd be like the four-color theorem. Check all these graphs, then you know if every graph is four-color.
All right. Thanks very much.
Thank you.